We thought leaving the solar system was just a matter of time. The physics says otherwise. You are never leaving the solar system, and neither is anyone alive today, and quite possibly neither is anyone who will ever be born. The reason has nothing to do with ambition or funding or courage, because the thing standing in the way is a wall made of distance and dust and nothing else. And carbon-based animals like us are badly suited to crossing it. What should bother you more is that the wall isn't ours alone. Every civilization out there sits behind the same one, which would explain a great deal about how quiet the sky has been. So let's talk about the barrier. Start with the thing our brains handle worst, which is scale. We evolved to judge two distances, right here and over the next hill, and everything past that collapses into one mental category called very far. That's why very far and a million times very far feel identical to us, even though the gap between them is the gap between a weekend trip and a project outlasting every civilization in recorded history. You cannot intuit your way out of this problem. You can only calculate your way out of it. So let's calculate, starting with speed, because speed is the only thing that converts distance into time. The fastest any human being has ever moved was on the way home. May of 1969, Apollo 10, falling back toward Earth from the moon at roughly 39,900 kilometers per hour, and nobody has beaten that number in more than half a century. It's fast in the sense that it crosses a continent in about 7 minutes, and slow in every sense that matters here. The reason we're stuck near that speed comes down to mathematics Konstantin Tsiolkovsky worked out in 1903, the same year we learned to fly at all. His rocket equation says that going faster means throwing mass out the back, and throwing more mass out the back means carrying more mass with you, which you then have to accelerate as well. The cost curve isn't a straight line, it climbs exponentially, which makes chemical rockets barely adequate for leaving Earth and completely hopeless for leaving the Sun. We did find one loophole. In 1961, a UCLA graduate student named Michael Minovich spent his summer at the Jet Propulsion Laboratory with access to one of the fastest computers on the planet, chewing on the three-body problem. What he found was that a spacecraft passing close to a moving planet can steal a sliver of that planet's orbital momentum and leave faster than it arrived, which is free energy borrowed from a world that will never miss it. We call this a gravity assist, and it's the only reason we've seen the outer planets at all. The Parker Solar Probe runs Minovich's trick harder than anything else we've built. 7 flybys of Venus, each one dropping the probe deeper into the Sun's gravity well, until December of 2024, when it hit roughly 690,000 kilometers per hour. That's around the Earth in under 4 minutes, and from here to the Moon in about 35. Now put a crew on something that fast and go exploring. Mars arrives in 2 weeks instead of 7 months, which is excellent. Pluto shows up after about a year, longer than you'd like, but survivable. 2 more years gets you across the heliopause, where the sun's wind finally loses its argument with the wind between the stars. And 1 more year past that, you overtake Voyager 2, which has been flying since 1977 and remains the most patient object our species has ever built. Everything up to this point feels like progress. Then comes the last stop before open space, the outer edge of the Oort cloud, that diffuse shell of ice which still technically belongs to the Sun. Traveling at 690,000 kilometers per hour, you arrive in roughly 2,500 years. That's the founding of the Roman Republic to now, and when you finally get there, you find nothing waiting. No station, no waypoint, no destination of any kind, just the place where our Sun's gravity stops being the loudest thing in the room. That's the barrier. Nobody guards it, it's simply empty. And it stays empty across an amount of space our brains refuse to hold. The obvious answer is to go faster, and it happens to be the right answer. We know of no non-magical way to beat the speed of light, and warp drives still demand exotic matter that may not exist anywhere. What we do know are physically permitted ways to reach a serious fraction of light speed, including fusion pulse propulsion, antimatter annihilation, and beamed light sail schemes like Breakthrough Starshot, where the engine stays home and the spacecraft is nothing but a mirror. Set the engineering aside, brutal as it is, and be generous, and say we get a ship up to 20% the speed of light. That comes to 60,000 kilometers every second. The edge of the solar system arrives in 3.5 days, the outer Oort cloud in 8 years, and Alpha Centauri in 20. All at once, the map opens up. Then, at 20% the speed of light, space stops being empty. It never actually was. The interstellar medium runs thin, roughly 1 atom per cubic centimeter in our neighborhood, and at ordinary speeds, that's a vacuum so hard we call it nothing at all. At a fifth of light speed, that same nothing turns into a particle beam pointed at your face. Run the numbers on a single iron atom. 56 nucleons arriving at 20% light speed carry about 1 billion electron volts of kinetic energy. And that's one atom. Back in 2017, Team Huang, Alex Lazarian, Blakesley Burkhart, and Avi Loeb worked through exactly what that does to a relativistic spacecraft. And the answer is that individual atoms punch damage tracks a fraction of a millimeter deep into the hull. This isn't erosion, these are bullet holes, delivered continuously, for decades, and your ship arrives structurally riddled. You can put a shield on the front, a sacrificial sail, or a slab of ablative material, something to eat the beam so the crew doesn't have to. That handles atoms. Dust is another matter. A single grain a micron across stops behaving like a particle and starts behaving like a bomb, dumping its energy so fast that it doesn't scratch the shield, it detonates inside it, flash vaporizing a crater and carrying shield material away with it. Every grain is a small explosion, and space holds a lot of grains. Above dust sit the pebbles. Take a golf ball, 45 grams, the least threatening object in human civilization, and hit it at 20% the speed of light. The relativistic kinetic energy comes out around 80 terajoules, which is the Hiroshima bomb with room to spare, arriving without warning, because nothing moving at a fifth of light speed can be seen coming in any useful way. Here's what turns this into a genuine barrier rather than an engineering headache. The damage doesn't scale gently with speed, since kinetic energy climbs with the Lorentz factor, while the rate you sweep up material climbs with velocity as well. So pushing from 20% to 40% of light speed doesn't double your danger, it multiplies it. Above some speed, no shield helps at all, because the shield gets destroyed faster than it can protect. Where exactly that ceiling sits is something we don't know, but we know one exists, and we know it sits uncomfortably close to the speeds we'd need. Be optimistic anyway. Assume heroic shielding. Assume the crew survives 20 years in a box without murdering each other, and you arrive at Alpha Centauri. That's where the third problem shows up, the one nobody wants to say out loud, which is that there's almost nothing worth going to. 4 years after arrival, the message reaches home, and humanity gathers to hear it. We made it. The planets are beautiful up close, and every single one of them will kill you. The astrophysics is superb, the food is not. Give a crew a realistic outbound life of 40 years at 20% light speed, and your reachable universe is a sphere 8 light-years in radius. Widen that absurdly and take the whole stellar neighborhood, a bubble 25 light-years across, which works out to 0.02% of the Milky Way. Inside it, you'll find a few dozen stars and a handful of brown dwarfs. Exactly 3 of those stars resemble the Sun, and one of the 3 is the Sun, while another is Alpha Centauri A. The rest of our neighbors are red dwarfs, small and cool and long-lived, and prone to flaring hard enough to strip the atmosphere off anything close enough to stay warm. Planets do sit in habitable zones out there. GJ1061d, 12 light-years away, makes a decent candidate. But habitable zone is a statement about the temperature at which water could be liquid, and nothing more than that. Mars sits in the Sun's habitable zone. Venus arguably sits at its edge, and the phrase promises far less than it sounds like. So here's the shape of the thing. The worlds we could actually reach are probably dead rock, while the worlds that might carry oceans and breathable air, the ones genuinely worth a human life, likely sit dozens to thousands of light-years out, which puts them behind journeys of centuries or millennia even at relativistic speed. A civilization far past ours could route around some of this. Solve senescence and a 300-year crossing becomes a long assignment rather than a death sentence. Send embryos in machines instead of adults. Build telescopes good enough to know what's there before you launch. Every one of those is at least conceivable. Look at what's left even then. Every colony you plant sits decades of one-way light away from every other one, which means no trade, no coordination, no shared politics, and no coming home. You wouldn't be building a civilization out there. You'd be scattering copies of one into the dark and never hearing back from any of them. The longer you look at deep space, the less sense it makes as a destination. The distances are absurd, the speed limit gets enforced by dust, and the places within reach may not be worth reaching, which makes space less of a frontier and more of a final exam, one we are nowhere near equipped to sit. Rockets, reactors, even fusion, all of it is hopelessly underpowered, and what's needed is something as unimaginable to us as a Saturn V would have been to a hunter-gatherer. Whether we ever get there is something nobody can answer, and it's worth remembering how badly this particular kind of prediction tends to age. On the 9th of October 1903, the New York Times ran an editorial titled, "Flying Machines Which Do Not Fly," estimating that powered human flight sat somewhere between 1 and 10 million years away. 69 days later, at Kitty Hawk, the Wright brothers left the ground, and 66 years after that, we were standing on the moon. So the honest position is this: the wall is real, the physics behind it holds up, and every argument here rests on what we currently know to be true. And that last clause is doing an enormous amount of work. Here's hoping this ages as badly as the Times did.